Welcome. In this video, we're going to talk about data structures, and in particular, we're going to talk about the distinction between linear and non-linear data structures, and we're going to delve into both the stack and the queue. So first, why do we want data structures? Why not just define any class as is and go on with our lives? Well, if we use abstract data structures, we have a way of structuring our information in a specific and generic way that can be shared across many different programs and many different patterns. As long as you're going to program, you're going to make use of data structures as complex or as simple as are needed in each example. Every data structure has a similar interface with predefined methods. So we can create the data structure with the constructor, we can access the data and modify it with getters and setters, and finally we can iterate through the data. That is, go through every element inside the data structure and apply some operation to it, or maybe just print it. So, if we have data structures instead of just classes, we gain the benefit of abstracting away the internal structure and the internal behavior of the method. The data structure gives us a general contract or general agreement on how the elements will be stored, how they will be sorted, what elements are acceptable, and what options are available to work with them. But the internal behavior and the internal representation of how we are actually storing these elements does not actually matter. Of course, it does matter because they can be quicker or slower depending on the case, but the outside interface, the methods that we call, will be all the same. We can split our data structures in many different categories, but the main data structures themselves are lists, which are a simple sequence, as you saw on the previous course. We can just store them sequentially and access any of them at any time. We can also use stacks, which work like a stack of plates or a stack of resumes. You can only see the element at the top of the stack, and you can add new elements to the top of the stack or remove elements from the top. We can also have queues, which work exactly the same as you think, like a queue of humans waiting for an event. And in this case, you can access elements at either end, but we typically access the first element and then we remove it once we're done with it, and we add elements at the end. Then we have sets in which the element ordering is not important. So, for example, a mathematical set in which you have a set of numbers or a set of people waiting to be sorted. And we can perform operations such as the intersection, the union, the difference, or just get a random element from the set. These sets are different from lists, stacks, and queues in that they do not allow repeated elements and that the ordering is not set in stone. So each iteration, the ordering might be different. Then we have dictionaries, which are very similar to sets, but instead of just storing a single object, they store a value associated to that object. So, for example, a dictionary would be represented as a dictionary, but we could also use it as a way to map objects to non-values. So, for example, we can map students to their IDs. And finally, we have graphs, which are a mathematical concept that we also use frequently, computer science, which represent a set of nodes connected via a series of arcs or edges. These structures can be classified into linear and non-linear data structures. So in linear data structures, there is an ordering established, and every element of the data structure is connected to the next and sometimes the previous element in the data structure. Of course, the last element has no following element, so it's connected to no one. And examples of this are the stack, the queue, and the list. And for nonlinear data structures, which we won't see in this course, we have graphs, we have trees, and we could also have sets depending on the implementation. So let's see a specific data structure. Let's go for the stack. To represent the stack, we're going to use a list from Python lists, which you saw in the previous course. Stacks use what's called the LIFO strategy, so last in, first out. The last element that has been put into the stack is the first, the one that becomes the top of the stack, and the one that goes out the first. And we have four main operations. To insert an element to the top of the stack, we call that to push an element to the stack. We can check what the element at the top is with the top operation, and we can remove the element at the top of the stack with a pop operation. So we push elements and we pop elements. And finally, we can always check whether the stack is empty or not to see if we can keep popping elements from it. Let's see a simple implementation using a list. First, we have a constructor which initializes an internal private attribute called items to an empty list. We're going to use this list to represent the stack throughout the class. We can always push elements, so we pass an attribute element to the push method, and in there we use the append method in the items attribute to add it to the list. So whenever we want to add an element, we just push it and that appends it to the list itself. We can pop an element from the list, and to that end we use the method pop from the items attribute. This removes an element and returns it to the user so that it can do as he wishes with it. Then we have the top method, which just checks the last element by using the index -1 in the items list, and we can always check whether the stack is empty. See that both the pop and top operations will fail when there's no elements, so we always have to check whether the stack is empty before calling them. Otherwise, we'll get an error. So let's see an example of the usage of the stack. So we can create a stack, we can ask whether it is empty, and in this case it's empty, and we can see the state of the stack down here. Then we can push elements, so for example we can push A, B and C, and they are accumulated at the top of the stack. And now we can check and print the stack itself and the top element, and we can see that the stack is A, B, C, with the C being the top element represented at the end. And then if we check the top, it will access the last element of this stack represented as a list, and we can see that is the letter C. We can always pop that element, and that removes it from the stack as shown here and returns it to us, and we can store it, for example, in the variable element. We can then print it and see that the element has been extracted, and then we can print the stack again with its top element, and in this case we can see that it's now B. If instead of accessing the last, the newest element, we want to access the oldest element, then we can use a queue data structure. So a queue is a sequence of elements that can be accessed in a FIFO strategy. So first element in is the first element out, and thus we respect a queuing behavior from humans or any object that we want to represent. We can always use the queue class in Python in the module collections, but we're going to implement our own, so you can see how we can implement this efficiently. Queues have two main operations that are called enqueue and dequeue to add and remove an element from the queue. Enqueue adds elements to the end, and dequeue removes elements from this beginning of the queue. And of course, as with most data structures, we can always check whether the data structure is empty. So let's see a short implementation with lists. Again, the constructor is very similar to that of the stack. We have a hidden instance variable called items with a double underscore. And then we have the enqueue and dequeue elements, which are very similar. The enqueue adds elements at the end of the list, and the dequeue operation removes the first element from the stack. This is not very efficient, but we'll see that on the next slide. Don't worry for now. And of course, the isEmpty operation has a very similar implementation to that of the stack. Let's see a short example with it. So if we have, this is our first version of the queue, and if we create a new object and we call it S, we can now print whether it's empty, and it is, and then we can enqueue three elements, and this would be these three buckets over here. When we enqueue the third element, we have A, B, C, and the first element to be removed will be A, because this one the first element in. First in, first out. Then, if we print the queue itself, we can see that the elements are here, and the first element to be removed will be the first one here, at the head of the queue. And now comes the tricky part. When we call the queue operation, this extracts with a pop, as we can see here, with a pop0 call, the first element from the queue. However, because this is implemented using a list, the pop operation has to perform two actions. First, it removes the element and gives it back, but then it has to move every other element such that the first element is now B instead of an empty location. So we have to move as many elements as we have, and of course, if we have a very large queue, this will mean that every time that we remove an element from the queue, we need to perform a very complex operation of moving elements throughout it. So let's see if we can fix this issue with an alternate implementation. Let's call it queue2. Our constructor is very similar. Our isEmpty check is very similar again, but this time we're going to use an insertion at the first position. So we're going to add elements to the beginning of the list, and we're going to remove elements from the end of the list. And this way our queue is reversed. So the pop operation is very simple. It's just pop without any parameters. But the insert operation, the unqueue operation, then becomes insert the element at position 0. And as the comment says here, it's inefficient. Let's see why. So if we create a queue from the queue2 class, we can create one, see that it is empty at the beginning, add 3 elements, and when in the adding operation is where we see the problem. See, when we want to insert at the first position, when it's empty, it doesn't matter, it goes in. But in the second one, then we have to move every element upwards and then insert the element, and so on and so forth. If we want to insert the C, we move every element up 1, and this is a linear operation, so it costs a small amount of time per value that we already have in the queue, and only then we can add the other element. The good news is that in this case, the removing elements from the queue is very, very cheap, because the pop operation only needs to remove the last element of the queue, and that operation is very, very cheap. You can see here that the elements have been represented in the same way, even though our queue is represented in the opposite way. That is because the external interface of the queue doesn't change, even though the internal representation does. In the next video, we'll see how to create a more efficient version of the queue using what it's called a linked list. But for now, you just need to know what the difference is between a stack and a queue, and how to make a simple implementation of it. And I'll see you on the next video.